Run your fingernail across Benjamin Franklin's shoulder. Do you feel those ridges? That's 20 tons of pressure hitting a secret blend of denim and linen. Most people think money is just paper and ink, but inside the U.S. Bureau of Engraving, it's actually a high-tech masterpiece that's designed to be impossible to copy. Today, we're breaking into the money factory to see how 4,000 tons of ink becomes $1 trillion. Most people call this paper. They're wrong. If you tried to print your own money on the paper sitting in your office printer, it would fall apart in a washing machine in seconds. The paper you're holding is actually closer to a pair of high-end denim jeans than a notebook. It is a masterpiece of material science, a fortress of security, and the most traded physical object in human history. To understand how a $100 bill is born, we have to leave the city of Washington, D.C. behind and travel to the dirt of the American South. The journey begins in the cotton fields of Georgia and the linen farms of the North. For over 140 years, a company called Crane & Co. has held the most exclusive contract in the world. They are the only people allowed to manufacture the substrate, the blank canvas of the US dollar. But this isn't just any cotton. To reach the durability required for a bill that will travel through thousands of hands, vending machines, and pockets, the cotton must have a specific fiber length. If the fibers are too short, the bill will tear. If they are too long, the ink won't bond correctly. The scientists at Crane & Co. monitor the soil pH and the nitrogen levels of these crops with the same intensity that NASA monitors a shuttle launch. When the cotton is harvested, it is sent to a high-security facility in Dalton, Massachusetts. Here, it is blended with 25% linen. Why linen? Because linen provides the snap. When you snap a fresh $100 bill, that sound is the vibration of flax fibers. These fibers are incredibly strong and resistant to moisture. While wood pulp paper is held together by weak hydrogen bonds that dissolve in water, the cotton-linen blend of a $100 bill is held together by a dense woven matrix of long-chain polymers. Inside the mill, the raw fibers are thrown into a digester, a massive multi-story pressure cooker. Most paper is bleached with chlorine to make it white. The U.S. government forbids this. If you bleach currency paper, it will glow under a black light, making it impossible to use UV security features. Instead, the fibers are cleaned using a proprietary alkaline process that strips away the natural oils and waxes without damaging the integrity of the fiber. As the slurry, a thick milky soup of cotton and linen, moves toward the paper machine, the first level of embedded security begins. This is the stage where the bill gets its bones. Imagine a giant machine the size of 2 football fields. This is the fourdrinier machine. As the wet pulp is spread across a moving wire mesh, a thin polymer ribbon is fed into the slurry. This is the security thread. It is important to understand that this thread is not glued onto the surface. It is positioned so that the wet fibers grow around it. On the $100 bill, this thread is encoded with microscopic text that reads USA 100. If you hold the bill up to a light, the thread appears as a solid dark line, but if you put it under a UV lamp, it glows a brilliant pink. This thread is the primary reason why bleaching a $1 bill to print a $100 bill doesn't work. A $1 bill has no thread. A $5 bill has a thread that glows blue. A $10 glows orange. The physics of the glow are tied to specific phosphors embedded in the plastic of the thread during the manufacturing process. These phosphors are tuned to a specific wavelength of light, making them nearly impossible to replicate with off-the-shelf chemicals. Simultaneously, as the paper is still 90% water, a dandy roll presses into the fibers. This cylinder has a relief of Benjamin Franklin's face embossed onto it. This is how the watermark is created. It is a common misconception that the watermark is printed with light-colored ink. It isn't. The dandy roll physically displaces the fibers, making the paper slightly thinner in the highlights of the face and slightly thicker in the shadows. When you hold the bill to the light, you aren't seeing ink, you are seeing the varying density of the cotton itself. This is why the watermark is visible from both sides of the bill. It is a physical part of the paper's anatomy. Now we come to the most expensive feature ever put on a piece of paper, the 3D security ribbon. That blue strip running down the center of the $100 bill isn't ink. It is a complex optical system. Inside that blue ribbon are hundreds of thousands of micro lenses. These lenses are so small that you could fit dozens of them on the head of a pin. Beneath the lenses are even smaller images of 100s and bells. When you tilt the bill, the lenses magnify the images at different angles, creating the illusion of movement. When you move the bill side to side, the bells move up and down. When you move the bill up and down, the bells move side to side. This is called parallax. To create this, the BEP had to partner with specialized physicists. The precision required to align 650,000 lenses with the microscopic printing underneath is a feat of engineering that rivals the production of computer microchips. Once the paper is finished, it is cut into massive sheets, 32 bills per sheet, and loaded into high-security currency crates. These crates are shipped via armored transport to either Washington, D.C. or Fort Worth, Texas. Upon arrival, the paper is placed in a humidification room. Because the cotton is organic, it breathes. If the air is too dry, the paper shrinks. If it's too humid, it expands. Before a single drop of ink can touch the surface, the paper must be acclimated for 48 hours to ensure that every single sheet is the exact same size, down to the micron. While the paper is acclimating, we move to the plate room. This is the most silent part of the factory. Here, the master engravers work. To become a master engraver at the BEP, you must undergo a 10-year apprenticeship. You start by drawing simple borders, then you move to letters. Finally, after a decade of practice, you are allowed to touch the portrait. Now we talk about the ink. The BEP produces its own ink in-house. The black ink used for the face of the bill is not just pigment and oil, it is magnetic ink. Inside the black ink are microscopic iron particles. These particles are what allow a vending machine or a high-speed bank counter to verify the bill. As the bill passes through a sensor, it generates a magnetic signature. If the signature doesn't match the specific magnetic profile of the Treasury's ink, the bill is rejected. Then there's the green. The green ink on the back of the bill is a proprietary blend designed to be highly resistant to chemical fading. You can soak a dollar bill in gasoline, bleach, or acetone, and while the paper might degrade, the Treasury green is formulated to remain steadfast. Before the first drop of ink hits the paper, we have to talk about siderography. In the world of high-security printing, this is the genetics of money. The master engraver has spent months carving a single portrait into a soft steel plate. But you can't print millions of bills from one hand-carved piece of steel. It would wear down in an hour. To solve this, the BEP uses a 19th century process called siderography. They take that hand-carved master plate and press it with a softened steel cylinder called a transfer roll with incredible force. This roll is hardened in a furnace. That hardened roll is then walked across a massive printing plate, stamping the image 32 times. This ensures that every single $100 bill on a sheet is an exact genetic clone of the original master. If you look at 32 bills under a microscope, the cross-hatching in Franklin's left eye will be identical to the nanometer. This is the first hurdle for a counterfeiter. They might draw one good face, but they can't create 32 identical perfect clones across a single sheet of steel. Now the paper meets the steel. This is intaglio printing. In your home printer, the ink is sprayed onto the paper.
In an office copier, the toner is melted onto the surface. In the money factory, the ink is forced into the paper. The printing plate is covered in that thick, magnetic black ink. Then, a massive wiper blade sweeps across the surface, removing all the ink from the flat parts of the plate but leaving the ink inside the engraved grooves. Then comes the impact. The cotton linen paper is laid over the plate, and a set of impression cylinders slams down with 20 tons of pressure. That's the weight of a fully loaded semi-truck concentrated onto a single sheet of paper. This pressure is so intense that it actually deforms the paper fibers, crushing them down into the ink-filled canyons of the plate. When the paper pulls away, it has been physically sculpted. This is why money has a texture. This is why, even if you were blind, you can tell the difference between a real $100 bill and a piece of photocopied paper just by touch. The ink isn't lying flat. It is a three-dimensional structure standing on top of the fibers. This is the tactile wall that counterfeiters simply cannot climb without a multi-million-dollar industrial infrastructure. The backs are printed first. The iconic Treasury green is applied in the same intaglio fashion. But here's the problem with printing with 20 tons of pressure and thick paste-like ink. It stays wet. If you stacked these sheets immediately, the green ink from the back of one sheet would smudge onto the face of the next. To prevent this, the sheets are moved into the drying vaults. The money must cure. For 72 hours, the sheets sit in a climate-controlled environment. The ink undergoes a chemical transition called oxidative polymerization. It doesn't just dry, it turns into a hard, plastic-like resin that is chemically bonded to the linen fibers. During these 3 days, the money is at its most vulnerable. It has the look, it has the feel, but it doesn't have a serial number yet. In the eyes of the Secret Service, this is unfinished stock, but to a thief, it's a gold mine. This is why the drying vaults are guarded by motion sensors, thermal cameras, and elite federal police 24/7. After the backs are cured, the sheets go through the intaglio press a second time. This is when the black ink, the magnetic ink, is applied. This is also when the optically variable ink is added to the 100 in the corner. This ink is the most expensive liquid in the building. It contains microscopic, multi-layered interference flakes. When light hits the ink at a 90-degree angle, it looks copper. When you tilt the bill to a 45-degree angle, the light waves interfere with each other and the color shifts to green. This isn't a shimmer like glitter. It is a precise physical phenomenon. Because the flakes must be perfectly flat and oriented in the same direction, the BEP uses magnetic fields to lock the ink flakes in place while they dry. We've talked about the texture and the ink, but now we have to talk about the invisible architecture. This is microprinting. To the naked eye, the border of a $100 bill or the lapel of Benjamin Franklin's jacket looks like a solid line. But if you take a high-powered jeweler's loupe, you will see that those lines are actually thousands of tiny repeating words. Why is this so hard to fake? Because of resolution. Most commercial scanners and digital printers work in dots per inch. When a scanner looks at a $100 bill, it sees those tiny words as noise. It tries to simplify them into a solid line or a series of fuzzy dots. But at the BEP, we aren't using dots. We are using physical grooves in steel. The ink-to-paper transfer is so precise that the letters remain sharp at a size that is smaller than a human hair. If a Secret Service agent looks at a bill and the microprinting looks like a smudge, that bill is a fake. Now the sheets are printed on both sides. They've been through the background offset, the green back intaglio, and the black face intaglio. They are beautiful. But are they perfect? Enter the Offline Currency Inspection System, or the OCIS. This is the most advanced computer vision system on the planet. As the sheets fly past at 30 feet per second, the OCIS takes a 400-megapixel photograph of every single square millimeter. It compares that photo to a master digital template. It's looking for errors that no human eye could ever catch. A tiny fiber of lint that fell onto the plate, a microscopic bubble in the ink, a variation in the registration of just 0.01 millimeters. If the OCIS finds a flaw, it doesn't just flag the bill, it digitally marks the exact coordinates on the sheet. The computer keeps a record of every single bad bill on every single sheet. This data is then sent downstream to the cutting machines, which will automatically divert the defective bills into the shredder. We are now at the end of part 1 of the money printing process.
These sheets are finished printing, they've been inspected, and they are now sitting in what the workers call the limbo vault. Technically, these aren't dollars yet. Why? Because they don't have a serial number. In the eyes of the law, these are printed stock. If you were to steal one of these sheets and try to spend it, you'd be caught instantly because the serial number and treasury seal are missing. Without those, it's just very expensive art. But the security in this vault is higher than anywhere else in the building. There is enough potential wealth in this room to fund a mid-side war. The workers who move these skids are tracked by RFID chips in their badges. Every time a skid moves, 3 separate signatures must be logged into the Treasury's mainframe. We have survived the fields of Georgia, the pressure cookers of Massachusetts, the 10-year apprenticeships of the engravers, and the 20-ton hammers of the intaglio presses. But the hardest part is yet to come. In part 2, we are going inside the Coke machines to see how a bill gets its social security number. We're going to explore the star note mystery, where broken money becomes a collector's dream. We'll see the massive industrial guillotines that slice through 10,000 bills at once. And finally, we will follow the armored convoys as they leave the factory and enter the global economy. The paper is ready, the ink is dry. Now it's time to make it legal. Welcome back. At this stage, we have what looks like money, but it's actually worthless paper. It's beautiful, it has the watermark, and it has the texture, but it has no legal identity. That changes at the Coke machines. This is the third and final printing process. Unlike the heavy, grinding pressure of the intaglio phase, this is a high-speed letterpress operation. This is where the Federal Reserve seals, the Treasury seals, and the serial numbers are hammered onto the sheets. Every serial number is a unique 11-character code, but it's not just a random string of digits, it's a digital fingerprint. The first letter identifies the series year. The second letter identifies the Federal Reserve Bank that ordered the money. The numbers in between are the production sequence. If that second letter is an L, that bill belongs to the Federal Reserve Bank of San Francisco. If it's a B, it belongs to New York. The ink used here is a specific Treasury green that is chemically distinct from the green used on the back of the bill. This ink is designed to be highly reactive. If a counterfeiter tries to wash the bill with chemicals to change the denomination, this green ink will dissolve into a bright purple or black smear, instantly flagging the bill as a fake. Now we have to talk about the broken money. Remember the OCIS laser inspection? If the computer found a microscopic smudge on one bill in a sheet of 32, that entire sheet is marked for destruction. But the Treasury is a bureaucracy of absolute precision. They cannot simply skip a serial number. Their accounting books must balance to the penny. So what happens when a sheet is shredded? They replace it with a star note. These are printed on separate replacement sheets. Instead of the standard suffix letter, they end with a 5-pointed star. Because these are only printed to replace errors, they are significantly rarer than standard bills. Some collectors spend their entire lives hunting for rare star note runs. In the world of currency auctions, a $100 star note from a low production run can be worth thousands of dollars. It is the only mistake the government allows to leave the building. Now comes the most dangerous moment for the bill, the great slice. Until this second, the money has been in 32 subject sheets. The Bureau uses a 2-stage cutting process. The first cut, the vertical slit, turns the sheets into half sheets. The second cut, performed by a machine with sub-millimeter laser guidance, slices them into the individual notes you recognize. The precision here is insane. If the blade is dull by even a fraction of a millimeter, it will pull the paper, creating a jagged edge. If the cut is off-center, the margins will look lopsided. This is a common giveaway of homemade fakes. Amateur counterfeiters rarely have the industrial hydraulic power to maintain perfect margins across a stack of 10,000 notes. Each blade is sharpened every 4 hours to ensure the crispness of the edge. The notes are now organized into straps of 100 notes. 10 straps make a bundle of 1,000 notes. 4 bundles make a brick of 4,000 notes. Let's look at the math of wealth. A single brick of $100 bills is worth $400,000. A single pallet of these bricks, it's worth $64 million.
These pallets are shrink-wrapped in heavy-duty, tamper-evident plastic and tagged with an active RFID sensor. This sensor is tied to the building's mainframe. If that pallet moves more than 3 feet without a digital work order from the central computer, the entire facility goes into a code red lockdown. Every exit is sealed by 4-inch thick steel doors in less than 2 seconds. The Bureau makes the money, but they don't own the money. As soon as those pallets are loaded into these trucks, they are legally handed over to the Federal Reserve. These trucks are virtually indestructible. They have run-flat tires, satellite tracking, and enough armor to withstand a literal grenade blast. They don't take a set schedule, they don't take the same route twice, and they are always watched by eyes in the sky. Their destination? One of the 12 Federal Reserve banks across the country. This is where the money is monetized. Until the Federal Reserve officially accepts the shipment, it's just inventory. Once they scan the pallets into their system, the digital balance of the U.S. economy goes up by billions. But for every new bill born, an old bill must die. The life of a $100 bill is about 15 years. The life of a $1 bill is only 18 months. When a bank sends soiled or mutilated currency back to the Fed, it is put through a high-speed sensor. If the bill is too thin, too limp, or too dirty, it is automatically rejected and sent to the shredder. The Fed shreds about 5,000 tons of money every year. In some cities, they actually give this money mulch as compost for flower beds or sell it in tiny vials as souvenirs. It's a sobering reminder, no matter how much work went into the engraving, the linen, and the magnetic ink, at the end of the day, it all returns to the earth. We live in a world of digital swipes and crypto ledgers, but the physical US dollar remains the gold standard of trust. It's a 19th century craft refined by 21st century science. The next time you hold a $100 bill, look for the watermark. Feel the ridges on Ben Franklin's coat. You aren't just holding currency, you're holding a billion-dollar engineering project designed to be the most secure object on the planet. If you enjoyed this deep dive into the world's most complex factory, make sure to hit that subscribe button.